Hello, students. This is Mr. Kraft coming to you from my house on this cold and snowy day. We talked about solving quadratic equations by completing the square yesterday, and that kind of brought up complex numbers, which we've touched on, but not a whole lot. So I want to talk about those today. So complex numbers are the last set of numbers that we usually talk about at this level of math. There are some others that you get to later on in graduate work in college, but that's not something that will be relevant to most of you all probably. So we start with various sets of numbers. We start with the regular numbers that we learn as a child, 1, 2, 3, which are natural numbers. And I'm just going to use a symbol. Hashtag also abbreviates for numbers. The double-backed N stands for the set of natural numbers. So then we add 0 to the mix, and then we have whole numbers, which we abbreviate with a double-backed W. Not a very well drawn one, but oh well. Then we add negative numbers. Which we abbreviate, well, I guess I should write their name first, integers. There are negative or positive, but there's no fractions allowed yet. So we use Z for the set of integers from a German word that means. So thus far, we've not had fractions. Natural numbers N, whole numbers W, integers Z. Then we go to anything that can be written as a fraction. And I'm not going to draw a whole lot of examples, which are rational or rational numbers. We symbolize those with Q, and there's a reason for that, which I don't remember off the top of my head. Rational numbers can be written as a fraction, which includes all of these, because, of course, any natural whole number or integer can be written as a fraction. Just stick a 1 under it, of course. Then you have the irrational numbers, which cannot be written as a fraction, which would be things such as pi or Euler's number, which is the basis of natural logarithms, which is not something we're talking about today, symbolized by E, and most square roots. Irrationals, if you write them out, are decimals that go on forever and never repeat, never end and never repeat. And I don't think there's a general symbol for those. So you got your that's not really a good drawing. So you've got your natural numbers, which is the set that is the smallest level of containment. Then they're inside the wholes, because wholes contain them. Wholes are inside the integers, because all whole numbers, this side of it, are integers. Then the outermost here is the rational, because all these guys can be written as fractions. Then separately, not overlapping, you have the irrational numbers, If it's irrational, it doesn't fit any of these. If it fits any of these, it's not irrational, so they do not overlap. And all of these guys put together are what we call real numbers, and we use the double-backed R to symbolize that. So you have natural numbers nested inside whole numbers, nested inside integers, nested inside rational numbers, kind of having irrationals over to the side, not interacting with them, and all of them are in the set we call real numbers. All right. Well, we've talked about imaginary numbers, the simplest of which is the square root of -1, or I. The square root of -1 is not 1, because 1 squared is 1. The square root of -1 is not -1, because -1 squared is also 1, because a positive times a positive is a negative, and a negative times a positive times a positive is a positive, and a negative times a negative is a positive. Now, it's true that -1 times +1 equals -1, but that's no good because these guys are different numbers. So, as I explained, I've talked about this in class before, the root of -1 is I, and technically it should be plus or minus I. We're not always picky about that, but, just so you know. So, mostly I'm going to worry about the plus or minus deal when I'm working with quadratic equations like I did in the last video. Here we're going to put that aside for a minute. Then, like I said, any negative number is just whatever the root would have been, I. So the root of 36 is a perfect square. Its root is 6. And since it's negative, 6i. And of course, plus or minus, we're not going to worry about that right now. -8, well, that's -4 times 2. You look for your perfect square. The square root of 2 does not change. The root of -4 is 2i. So 2i root of 2, plus or minus technically. And in this case, 7 can't be rooted at all, so we just pull out I and leave it as it is. Simple as that. And then if you had something like 3 over the square root of -5, that's a rationalization exercise. You just say the denominator over itself times the original. Has to be over itself because that means it's equivalent to 1, so it's not changing the original fraction, just changing its form. The square root of -5 times the square root of -5 just clears, and you get -5. And then you get 3 root of -5 on top, which is 3i. The negative part comes out as an I. And then, I've said this before, but I'll review it. Technically, the best way to write a negative fraction is that. But it's the same thing as this. It's the same thing as that. This is the best way to write a negative fraction because the one part is not really negative and the 2 positive. The one's not positive and the 2's negative. The whole thing is negative. If you had a number line, and here you had positive 1/2, and here you had negative 1/2, the whole fraction is on the left-hand side. But in handwriting, it would be easy to run these together, and that just looks horrible and ugly. So we usually put the negative sign when we're handwriting it on the top. So this negative that goes on the 5, I'm going to slide up, and this is what that becomes. That's Did not mean to do that. So 3 over the square root of negative 5 becomes negative 3i square root of 5 over 5. Just keep making all kinds of marks here. Okay, what I want to talk about is not just the imaginaries, but the complex, which I've touched on before, but I want to kind of talk about them again. Like I said, if I can make a straight line for a change, if you put your x-axis, you know, we're used to thinking of this as x and y. In complex numbers, we let the x-axis be the real axis, the numbers we're used to dealing with. 1, 2, 3, 4, 5, 1 half, 1/3, 1/4, negative 1 half, negative 1/3, negative 1/4, what have you. These guys are imaginaries, so you have I, 2i, 3i, 4i, 5i, and likewise going downward, you have negative I, negative 2i, negative 3i, negative 4i, negative 5i. So with your standard graph with XY coordinates, you know, on the edge of this tablet is hard to draw. I'm making some appallingly ugly graphs. Let me see if I can make it a little bit nicer. So you have your X coordinate and your Y coordinate. So if you had 1, 2, 3, 4, I'm not going to put the negatives in, but they're there. If I had a point, the point has 2 coordinates, an ordered pair. You know this already. You do the X coordinate first. It's 3 units out, 2 units up. So the X coordinate is first, followed by the Y. So the coordinates are 3, 2. Well, you know what? Complex numbers. Complex. And the set of complex numbers, we use double-backed, or whatever you want to call it, C, to mean complex. Instead of using an X coordinate and a Y coordinate, we use a real number and an imaginary number. So right here would be 3 plus 2i. You have the real component added or subtracted to the imaginary component. So over here, you would have 3 minus 2i over 3 down 2i. Here, you would have negative 2 plus 2i. They're always separated by addition or subtraction because real numbers and imaginaries are about as apples and oranges as you can get. You can't add them directly. And then say you have negative 4, let's see, go here. Negative 4 plus, I'm sorry, not plus. Negative 4 minus I. You're over 4 and down negative I. So, a complex number, you have a real part plus an imaginary part. That's a double-backed I. That's not the Roman numeral 2. So you got real plus or possibly minus imaginary. So 3 plus 6i is a complex number. 5 minus 8i is a complex number. negative 7 minus 15i, or negative 12 plus I. These are all complex numbers. Well, that brings up a question, 5i. There's no real part. So is it complex or is it strictly imaginary? Well, the answer is you could say the real part is just 0, 0 plus 5i, so ding, 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 ding. It does belong to complex numbers. If you remember, this symbol means element of or belongs to. So yeah, this guy belongs to the set of complex numbers. What about 33? Looks like a plain real number. But you could say it's 33 plus 0i. So ding, 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 that belongs to complex also. So to go back to what we said earlier, you've got your whole number, your natural numbers or counting numbers. Then that goes inside your whole numbers. You just add the number 0. That goes inside your integers, and which includes negative numbers. And that goes inside your rationals. And then your irrationals do their own thing. They're the cool kids. They don't hang out with everybody else. And then all of these guys together are real numbers. Well, now we have the biggest category of all, which is the complex. You have the imaginaries over here. Then when you add or subtract them to somebody over here, you have complex. So complex numbers are the biggest set of all. Now, let me show you how to add and subtract complex numbers. We'll save multiplication for a later date because I think I've laid enough stuff on you as it is already. All right, so if I had 3 plus 6i, and then I had 5 minus 2i. I want to add those guys. Easy peasy. Real number parts add to each other. Imaginary parts add to each other. 6i minus 2i is 4i. Boom. Easy. Super easy. So if I had 3 plus 3i plus 7 plus I. 3 plus 7 is 10. 3i plus 1i is 4i. 10 plus 4i. Easy. I'm not even going to do any more of those. They're so easy. Suppose I had 6 minus 8i minus 5 plus 2i. And I'm putting these in parentheses from this point on so it's clear that these are separate units. Well, this is very easy too. You've done things like this before many times, except instead of having i's, you had x's or y's or z's or other variables. You just distribute. Negative times a positive is a negative. Negative is a negative. Now, 6 minus 5 is 1. Negative 8i minus 2i is negative 10i. Boom. You've got it. If you had something like 7 plus 5i minus 3 minus 7i, well, once again, the first one's not changed. Negative times a positive is a negative. Negative times a negative is a positive. So 7 minus 3 is 4. 5i plus 7i is 12i. 4 plus 12i. Easy as that. This is a lot of stuff that I've covered in this video. I'm going to leave it at that. We'll talk about multiplying imaginary numbers the next time, which will actually be easier than you think it might be, but we'll talk about it then. Meanwhile, I'll talk to you later. Goodbye.